Grade 11s, thank you for joining me today. My name is Gillian and we are discussing physical science. Today is a really interesting topic. It's important. It is a type of reaction, and that is the acids and bases. So it's quite a big section. We are going to be looking at the big ideas around acids and bases, and those ideas, those theories that you really need to carry forward to grade 12. Okay, so let's have a look at the overview and we can pick out what we're going to be discussing today. So on my screen, we have chemical change, reactions in aqueous solutions, and part of that is the ion exchange reactions. We have already discussed precipitation. Now we are going to highlight acids and bases. We discussed last time what dissociation looks like and what ionization looks like. And guess what? Those come up again in acids and bases. So the overview of these reactions in aqueous solution is done. Now let's have a look at the chemistry of acids and bases. So we have at the beginning, or at the base of this, we have an acid-base theory. Now, there are two guys that have influenced the chemistry around acids and bases, and one of them was Arrhenius, that dude over there, Arrhenius. That was around about 1884 that he came up with his theory. It was then discovered that his theory had limitations, and so two individuals in opposite sides of the world came up with a different theory, and it's named after their surnames, Bronsted and Lowry. And so we're going to have a look in detail at what they said. Now, when we look at acids and bases, we have to look at how we can measure them, and that is the pH scale. So the pH scale is part of our theory, and we look at what do we consider to be a weak acid, a strong acid, a weak base, a strong base, and how can we tell? So that's the pH scale. Then we have types of reactions that take place for an acid in particular. And those reactions are quite exciting, some of them, and very important. So the one is neutralization. The second one is metal oxide. So what happens when an acid reacts with a metal oxide? And then we have metal carbonate. Now there's one that you have come across before in your science curriculum, and I haven't written it down here, so I'm going to add it, and that is when an acid reacts with a metal. So that pops up every now and again, so we need to have a look at that. Rightio, let's continue. So let's have a look at this pH scale. So pH scale, if you have a look at that word, H is telling you about how acidic something is. The H represents the amount of acidity that a substance will have. There is a range. So it starts at 1 and it ends at 14. Now, in the middle, you see I've drawn a line there, it is 7, and so that is considered to be neutral. Okay, neutral. Now, a strong acid is going to fall in this area here. So 1 to 2, maybe a little bit onto 3. So that's a strong acid. Will have a value of between 1 and maybe 2.5. A weak acid will fall in between the 3 and the 7, so that's going to be weak. When we move over to bases, a strong base will be on this side, will be on the opposite side of the scale, so that will be a strong base. And it's around about between 12 and 13 to 14, around about there. The in-betweener from 7 to, let's say, 12 is going to be a weak base. So now this scale is just a scale, so there is a value to it. It is a comparison. So we're comparing the solution or the acid or the base, and we're saying, well, what is the concentration of the H plus ion in it? So if there's a very big concentration, if that substance, if it ionizes to completion, then it is a very strong acid. If it doesn't, if it's incomplete ionization and those particles don't like to release the H plus ion, then it is a weak acid. When we move over to the basic scale, so the scale telling us that we have a base and not an acid, we see a similar thing, that the dissociation of the base is almost complete or complete for a strong base, and then for a weak base it's not very complete. It's an incomplete dissociation. So we're going to be speaking about that further on when we classify a weak and a strong acid and a weak and a strong base. Moving on to our next big idea are the acid-base theories. So what did Arrhenius say? So Arrhenius looked at an acid and a base, and he looked at them in water. So that's really important. In my picture here, you can see water. It was in an aqueous solution. And he said that there are ions produced, and the ions are the H plus ion and the OH minus ion. And that OH minus ion is called the hydroxide ion. So that's what he spoke about, and he was looking particularly at neutralization. So neutralization is where we have the acid component and the base component almost cancelling each other out and creating a neutral solution with a pH of 7. Okay, so it was the interaction of these two ions, the H plus and the OH minus ion, to form a neutral solution. There were limitations to this, and the limitations were the following. Although Arrhenius could explain what was happening, the behavior of the acid and the base in an aqueous solution, he couldn't explain when the solvent was different. So his theory could not explain what was happening when the solvent was not water. The other thing that he could not explain was with his saying that this is the behavior of an acid, it produces H plus ions, and this is the behavior of a base, it produces OH minus ions. He couldn't explain if there was something else being formed. For example, this oxonium or hydronium ion, H3O plus, it's a different chemical, and he couldn't explain that with his theory. So these two guys, the Bronsted and Lowry, they looked at the behavior of acids and bases in a completely different way. So they spoke about the hydrogen plus ion. So if we look at my picture here, we know that hydrogen is the first element in the periodic table. It has got one proton and one electron. So if we draw in my electron here, there we go, the electron of hydrogen, that is what it looks like. Now, if we take that electron away, it then becomes the H plus ion. There we go, the H plus ion. But what in effect is that really? Well, what's left behind is a single proton. It's a single proton. So what Bronsted and Lowry said was, instead of classifying acids and bases according to what they do in an aqueous solution, we are going to classify it according to whether they give away a proton or whether they accept a proton. So their theory is based on the transfer of protons. In other words, this little positive charge that used to be a hydrogen and has now lost its electron, and that's all it is. It is just one single proton. So they said that an acid can be classified as an acid if it donates a proton. so it donates a proton. So it gives away a proton, gives away an H plus ion. What about the base? Well, they said a base is the substance which accepts the proton, accepts it, takes it in. So a base is known as the proton acceptor. Now, this whole process happens simultaneously. So as the acid donates the proton, so the base accepts the proton. And this whole process is called protolysis. And that makes sense. It links into the name of transfer of protons. Right, so let's look at these two kinds of reactions. The one is a dissociation and the other one is ionization. So ionization is the reaction. Dissociation is where there's a split of a solid, an ionic solid, into its component ions. So the first one is ionization. Ionization happens with covalently bonded molecules. There we go, covalently bonded molecules. It actually interacts, this covalently bonded molecule interacts with the water molecule. And we see here we've got hydrogen chloride. It is an acid. And we say hydrogen chloride, its formula is HCl. And we could also have another name for it, which is hydrogen chloride. So hydrochloric acid, hydrogen chloride, HCl. It interacts with water in the liquid form, in the liquid phase, and what happens? Well, the hydrogen plus ion, the proton, is donated to the water molecule. So that's why I'm saying that HCl is an acid, because it is actually the proton donor. And so the proton donor in this case is HCl. Hydrogen chloride or hydrochloric acid. It forms this interesting ion here, which is called the hydronium ion, the H3O plus ion, the hydronium ion. So, proton donor is the hydrochloric acid or HCl, hydrogen chloride. Why is it called acid? Because it donates the proton to the water. Grade 11s, it's time for a break. See you just now. Welcome back, grade 11s. We're busy with the ionization of covalently bonded molecules in water. We've already decided what the acid is, and now we need to have a look at the base. So, a base, according to Bronsted-Lowry, is the substance or the molecule that takes on the proton. So it is a proton acceptor. So if we look at our screen, we can see here that water is the molecule that has taken on that proton. And it has become this particle here, this ion here, the hydronium ion. So it is the proton acceptor, and we can write down there that the proton acceptor is the water molecule. Now I've written here, is it a strong or a weak acid? Or is this a strong or weak? So we've seen tables of strong and weak acids. We've also seen tables of strong and weak bases. So what tells me that HCl is a strong acid? The thing that tells me that, besides learning it from the table, is that there is complete ionization of this covalent molecule. What does that mean? It means that almost all of the hydrochloric acid molecules will ionize. So if we look at our container, our reacting container, at the end, we will see that there are very, very, very few HCl molecules there. In fact, most of them will be hydronium ions and chloride ions. And so we say that this ionization is complete. And for that reason, the arrow is quite a definite, strong arrow in one direction. And that is telling us that this is a complete ionization. Complete ionization, strong acid. Let's move on now to dissociation. So dissociation happens with an ionically bonded substance. We can see we've got sodium hydroxide, and when it is placed in water, it breaks apart into sodium plus ions in the aqueous state and hydroxide ions. So this is the hydroxide ion. Now, how do we tell whether this is a strong base? Well, we know that it is a strong base because there is complete dissociation. In other words, that sodium hydroxide salt is completely broken apart by the water into its component ions. You will not find a lot of the solid particles, the particles of sodium hydroxide in the reacting vessel or the vessel. You will see that most of it will be sodium plus ions and hydroxide ions. And so there's complete dissociation. How do I know that this is a base? I know that this is a base because according to Arrhenius, a base will produce hydroxide ions in solution, so in an aqueous solution. So you make use of both of these theories because they are both true in certain circumstances. So in this circumstance, when we've got sodium hydroxide in water, it's in an aqueous solution, we can use Arrhenius's theory. So sodium hydroxide is going to be a strong base because it dissociates completely. What about acids and bases that are weak? They are weak because either the dissociation or the ionization is incomplete. So I have here on the board this interesting molecule, acetic acid or ethanoic acid. It's got two names. It is an organic molecule, and it is a weak acid. And I know it's a weak acid because it does not dissociate properly or nicely. It doesn't dissociate completely to form a high concentration of oxonium or hydronium ions and this ion over here, the anion. It likes to be as its original molecule. And so when I write this equation, I actually add a little arrow to that side as well. And that arrow is telling me that actually this ethanoic acid likes being in that form. It is incomplete ionization, and because it's incomplete ionization, it is a weak acid. Let's have a look at an example of a base which is a weak base. So here we have an example which is magnesium hydroxide. Magnesium hydroxide actually doesn't like dissociating. It likes being like that, magnesium hydroxide. And so it doesn't dissolve very nicely in water. The concentration of the magnesium 2+ ions and the hydroxide ions is quite low. It doesn't like being in that form. It rather will sit to the other side. It will like being in its magnesium hydroxide form. And because this dissociation is incomplete, it is a weak base. So we're really talking about the extent of dissociation. What is it? Is it complete or is it partial? If it's partial, it's incomplete, and that it gives us a weak base. Now, I love this molecule. This is ammonia. Ammonia is a real rebel. Ammonia does not do what we would expect it to do. It breaks all the rules. So ammonia is covalently bonded. If we look at all the other covalently bonded molecules, other covalently bonded molecules, they ionize, and they ionize completely, or they ionize quite well to completion. This molecule, this ammonia, doesn't. So even though it's covalently bonded, it really does not like going to complete ionization. And the other thing about it is a base. How weird is that? So if we have a look at this equation, we will see that this ammonium ion is formed and the hydroxide ion. Look at that. The hydroxide ion is formed. According to Bronsted-Lowry, let's see whether it does actually fit the profile of being a base. So remember, a base is a proton donor. A proton acceptor is the base, according to Bronsted-Lowry, a proton acceptor. And so here, it starts off as NH3, it ends up as NH4+. So what has it done? It's actually accepted a proton from water. So it is a proton acceptor, which means that it is a base. How odd is that? So that is one molecule you must learn. Right. An amphilytic substance is a substance that can behave as an acid and as a base. And you'll see here, there's something which is water, which does both. And so in this first reaction, we've just seen it with ammonia, it acts as an acid because it donates a proton to the ammonia. And in the second reaction, it acts as a base because it is accepting a proton from hydrochloric acid. So you can see that the water molecule is behaving as an acid in one circumstance and as a base in a different circumstance. These words here, monoprotic, diprotic, and triprotic, they refer to the number of protons that are donated. So, for instance, diprotic, if we've got an acid which is H2SO4, it is going to donate 2 hydrogens. So 2 protons it will donate, and therefore it is di. There are quite a few monoprotic acids, and you can have a look and see which ones are triprotic as well. Now, conjugate acid-base pairs. This was part of the theory of Bronsted-Lowry, and we have to look at the reaction in both ways, so in the forward way and in the reverse way. So let's have a look. Let's first analyze the forward reaction, what is happening here. So we've got hydrogen carbonate, that's that one there. It ends up as this ion. What is happening with it? Well, it started off with 2 hydrogens, and it has ended up with only 1 on that side. So what is it doing? It is donating a proton to water. So that means that this is the acid on this side. If we look now at the reverse reaction, so if we consider these to be our reactants, so we're just reading it backwards, reactants, and we're looking at the reaction in that direction, what is happening? Well, it starts off as HCO3 minus, and it ends up as H2CO3. So what has it done? It has accepted a proton from the oxonium ion or hydronium ion. So there we go, it's accepted a proton. So if we're looking from the forward reaction from this side, from the left side to the right side, it is an acid. If we're looking at the reaction from the right side to the left side, it is a base because it is a proton acceptor. Now that is what we call the conjugate acid-base pair. So this will be the conjugate acid-base pair. There's the acid on that side. Here is the base on this side. We have 4 reactions with acids. Neutralization, and that is an acid and a base what do they form? They form a salt and water. So that is a general equation that you need to know. What about metal oxides? So now we're taking the acid and we are reacting it with a metal oxide. And the same thing happens. How interesting is that? So we get a salt being formed and water. This one, metal carbonate is a gas-forming reaction. So a metal carbonate is quite distinctive when it reacts with an acid. It forms a salt plus carbon dioxide gas and water. Grade 11s, I've added the metal. So an acid reacts with a metal, and it also is a gas-forming reaction. The product is going to be a salt plus hydrogen gas. There we go, that's the gas. So grade 11s, we've come to the end of our time. We will look at some of these reactions in greater detail in the consolidation lesson when we have a look at problems and questions that are being asked. So please join me then. See you later.